Good morning, everyone, and welcome to EDP and Applied Mathematics Seminar. It's a pleasure for me to open session 50 of this seminar. Today we have two excellent speakers, Aissa Guesmia and Carlos Guzman. Introducing Aissa Guesmia, we have the Professor Mauricio Sepúlveda. Thank you, Mauricio. You can start.
Okay, thank you very much, Juan. It's a pleasure for me to present my colleague and friends, Professor Aissa Guesmia, which is professor of the University of Lorraine, Metz in France. He's an expert in PDEs, controllability and stability of dissipative equation. And now, today, he will talk about some well-posedness and stability results for thermoelastic Bresse-type system with different kind of heat conduction via the vertical displacement. Please, Professor Aissa.
Thank you very much, dear Mauricio. Thank you very much, Professor Limaco, for the invitation to give a talk in this seminar. It is really a pleasure and honor for me. So as is indicated in the title, I will present some well-posedness and stability results for Bresse-type systems with the dissipation generated by heat conduction, which is working or effective on the first component of the Bresse system, which describes the vertical displacement. Some results of this talk were obtained in collaboration with Munir Afilal from Qadi Iyad University in Morocco and Abdelaziz Soufiane, University of Sharjah, Emirates. This is the plan of my talk. So first, I will start by giving an introduction. I will present the problem that I will consider here. I will indicate some new results in the literature, and I will fix my objectives in this talk. The second part concerns, well, the well-posedness of solutions, so existence, uniqueness, and smoothness solutions. This will be done by formulating our system in a first-order system and applying the classical semi-group theory. In the third part of my talk, which is the main part of my talk, which concerns the stability problem. So I will speak about four kinds of stability results: exponential stability, non-exponential stability, polynomial stability, and strong stability. I will try to give some ideas of the proofs because, well, the proofs are very technical, and I will finish my talk by giving some issues and open questions. This is the system I consider here. It is known as a circular arch problem, which is mathematically three wave equations in a bounded open domain in one-dimensional case with a coupling terms of order 1 and 0. That is, we have the coupling terms, which sometimes we have derivative with respect of x and sometimes without the derivative with respect of x. So we have three wave equations with, of course, this is boundary conditions. Here we consider Newman boundary condition, homogeneous Newman boundary condition for in the first component, and the homogeneous Dirichlet boundary condition for the other components with initial data. And here we have b theta, which is this term generates, well, the dissipation on the system, and it is effective only on the first equation. That is on phi, which describes the vertical displacements, while psi describes the shear angle displacements, and w describes the longitudinal displacement, and theta is the temperature. Well, of course, phi 0, psi 0, etc. are initial data, and the parameters q1, q2, etc. are positive number, which is represent some physical parameters of the model. Here I consider four kinds of heat conduction. So the first one is known as type 1 or Fourier's law. So this term b theta is equal delta theta x, and theta, the temperature, is given by this wave equation, which depends only on phi. So depends on the first equation of, or first component of our Bresse system with initial data theta 0. The second one is type 3, known as type 3. So here, while the temperature is given by a wave equation, also we have, well, initial data, of course, and this coupling term with the first component of Bresse system. The third heat condition I consider here is known as Gerten-Pipkin's law. So B theta is always delta theta x, and theta is given by this equation where we have this infinite memory depending on this kernel f function f. Here we remark that in this particular case the initial data of theta depends also on t, so the integral between t here and the plus infinity, so we get t minus s is negative. So in this case the values of phi are known from the beginning thanks to this theta 0 which depends on t. And the last heat condition I consider here is known as second sound or Catanius law. So the temperature theta is given by these two equations when Q is the head heat flux, and we have here, well, this coupling terms. Here, the parameter delta and gamma are not necessarily positive, are, well, non-real, which is different to 0. The function f satisfies this condition, so we put g equal to minus f prime, and we assume that g is in C1, r plus, satisfies these two inequalities, and the integral is strictly bigger than 0. The integral is strictly bigger than 0 means that g is not identically equal to 0. So we have, well, this memory term is present, is not equal to 0. So if we integrate these two inequalities, we prove that g is satisfies these two inequalities, which means that g converges exponentially to 0, 1s converges to plus infinity. So as I indicated in the beginning, the heat condition B theta plays the role of dissipation, and it is effective on the first equation, vertical displacement of, which describes the vertical displacement. The other two equations, the second and third ones of system P, are free, are not directly controlled. They are just indirectly controlled via the coupling terms with the first equation. If B is equal to 0, that is, we don't consider this term B theta, is known that P is conservative system. So as we will see later, its energy is a constant function. So to get the stability, so to force the solution to converge to 0 when t goes to plus infinity, we need to add something, to add a control. So here I am interested in this kind of controls given by heat conduction. In the particular case where W equal to L equal to 0, that is, we don't consider the third equation of P, the system P is reduced to well-known Timoshenko type system, and the stability in this case using different kinds of controls, heat conduction or frictional damping or memory, finite or infinite memory, internal or boundary, etc. These questions are widely studied in the literature. Here we have just some examples of papers, some people who consider this kind of problems. The list is not exhaustive, and there is various stability estimates depending on the number of and position of dissipations. When in the case of P, where at least the second or third equation is directly controlled, so we put a control on at least on the second or third equation. Also, there are situations were treated by many people. So here I indicated just some examples, papers using not only heat conduction but frictional damping, memory, etc. And also we have in the literature different kinds of stability estimates depending on the control and the parameters of the system, etc. But what we remark in these two cases, that is, when we have at least a control on the second equation or the third equation, we have always the exponential stability in some situations. So when the first, the second, and the or third equation is controlled, we have some connections or some conditions which guarantee the exponential stability. This is the main difference between that situation and the situation that I consider here, that we have only a control in the first equation. As we will indicate later, we prove later, in some cases, we don't have the exponential stability. So here, this is the objectives of this talk. For the well-posedness problem, so I will fix a Hilbert, define a Hilbert space H, and formulate the 4 cases in abstract first order system, capital P, and prove that, well, the operator describing this system is maximal monotone operator. So it generates a semigroup of contraction, linear semigroup, because, well, we'll see that the operator is linear. And then we apply semigroup theory to get, well, some well existence, uniqueness, and smoothness of solutions. For the stability problem, which is the main question I consider here, in case 1 and 2, in cases 1 and 2, heat conduction of type 1 or type 3, we prove that the exponential stability does not hold, whatever the parameters are. In the other 2 cases, that is in cases 3 and 4, heat conduction of Gerten-Pipking or second sound type, we give or we obtain, well, necessary and sufficient conditions for the exponential stability. In the other cases, that is where we don't have exponential stability, we get the polynomial stability for initial data in the domain of the operator A, and strong stability for initial data in the space H. Here we have, well, the definition of the exponential stability, polynomial stability, and strong stability. So here we have the norm of UT, the norm of the solution of this abstract form system P, smaller within quantity, so it converges exponentially to 0. Here converges polynomially because we have t power minus C2. C2 is positive. And the strong stability is just the solution goes to 0 when t goes to plus infinity. So here we have, well, I indicate the papers where those results were published. So the cases type 1 and type 3 were treated by myself, and the results were published in Applicable Analysis 2 years ago. The case of Gerten-Pipking, case 3, is obtained or treated by myself and submitted submitted paper. And the second sound is joint work with Munir Afilal and Sufyan Abdulaziz, and also is submitted actually. Well-posedness. First, in the case of in case 3, that is Gerten-Pipking's law, to treat this infinite memory, we use this new variable eta with its initial data. This is well known as Dafarmos variable, introduced almost maybe 40 years ago for the wave equation. And this variable satisfies this partial differential equations, thus initial conditions, and our term, the infinite memory, which appears in the case of Gerten-Pipking's law, can be written in terms of eta, this new variable, but here instead f we have g, where g is minus f prime. Here this is with the norm of L2, and the space of H noted LG of eta, sorry, noted LG is given, well, by classical definition. This is really classical things, where H1 0 is classical Sokolov spaces V in H1, so that V0 equal to V1 equal to 0. Now, so we introduce these two spaces, L star, it is the V in L2, so that the average is equal to 0. H star is the element V in H1, so that the average is equal to 0, or H1 intersection L star. And we define our Hilbert space, which is named or known as the energy space for our case. It's H star, L times L star H10 times L2 times H10 times L2 times H. And this space H is defined here. So it depends on the situation. Type 1, so U is the first component of Bresse system. Its derivative with respect of time t. The same thing for psi, the same thing of W and theta. So the space of theta is L2, the space of phi is H star, etc. Here, why we consider H star and L star for phi and phi t? Because if you remember, for the phi, we considered Newman boundary conditions. However, for the psi, W, and theta, we considered directly boundary conditions. So for this reason, we consider these conditions, the integral of V is equal to 0, to be able to apply Poincaré's inequality. And this is without loss of generality, because by change of variable, we can assume this condition, okay? For type 3, we add theta and theta t. So the space of H and theta t is H10 and L2. For Gerten-Pipkin's law, we add theta and eta. This the variable eta introduced by the Fermat, and the space of eta is L2, the space of theta, sorry, is L2, and eta is Lg. For the second sound, we have theta, we add theta and the q, and the space is here, and we arrive to write or to formulate our the four cases in this first order abstract system with linear operator A, given by this formula. Here we have two lines, and here we have a constant or q degree of derivative. So here we have the definition of q and the line. So in case of type 1, q equal to 0, L1 is this, and L2 is not considered. We have only the line L1. For type 3, q1 is 1, L1 is this, L2 is this, etc. For Gerten-Pipkin, q is 0, L1 is this, and L2 is this. And for the second sound, we have q0, L1, and L2. Now we define, well, the domain of A power n for n in n, for n in n by a classical way. So domain of A star, that is A power 0, that is the domain of the identity, is H. The domain of A is this. So here we have to add the Newman boundary conditions, and well, this initial condition on eta, because if you remark from the definition of eta, when we put s equal to 0, we get exactly 0, because eta is the integral between t minus s and t. So when s equal to 0, we have eta equal to 0. And for n equal to 2, 3, etc., we have the definition of d power n. On H, we define this norm. The norm square is this quantity plus one of this term, depending on the cases we consider. And the inner product on H is the one generated by this norm. So this is the well-posedness result. So for any n in n, for any u0 in the domain of A power n, our abstract first order system P has a unique solution which has this or satisfies this regularity. So here we have a connection between the regularity of the solution and the regularity of u0, describing by n. So for example, for n equal to 0, that is u0 in H, so we get only u is continuous on H. This is weak solution. For n equal to 1, u0 in the domain of A, so we get solution which is continuous on the domain of A and of class C1 in H. So, and etc. We have this general connection between the regularity of initial data and the regularity of the solution. So to prove this, we have just to prove that A is generated a semigroup of linear semigroup of contraction on the Hilbert space H. To do so, we prove that is first A is dissipative. So this just we have to prove that this quantity is negative, but this is equal to this. It depends on the cases, and we see that in each case this is negative or not positive, because Q4 is positive, Q5 is positive, G prime is negative. Well, thanks to the hypothesis on G, and this here minus Q4 is negative. The second thing we have to prove is that, or we prove that a minus 1 exists on H, and then by classical argument, we conclude that lambda I minus A, I is the identity operator, is surjective, and then we conclude that A generates a linear contraction semigroup on H, and the injection of the domain of A in H is dense and compact. So our domain is 0, 1, is bounded, open bounded. Also, we can consider any interval 0, R, but with those laws of generality, we consider 0, 1. Now we go to the main question I consider here, which is the stability question or the stability problem. This is the exponential and non-exponential stability results we have. So for type 1 or type 3, the exponential stability of P does not hold independently of the parameter. That is, these two kinds of heat conduction are not strong enough to provide the exponential stability of P. However, in case of Gerten-Pipking and second sound, we have the equivalence between the exponential stability of P and these two conditions. So we have here a condition on L2, L square. L, it's this parameter which appears on the Bresse system. We have Q2 is different or different to Q3. So it means that, well, the speeds of wave propagations of the second and third equation of Bresse system are different. And delta square, delta is the parameter which represents the coupling terms between the heat conduction and the first equation of Bresse system, satisfies these two equalities, where Q0 is F0 in case of Gerten-Pipking law, and Q0 is equal to 1 in case of second sound. So we have the equivalence between the exponential stability of P and these two hypotheses, H1 and H2. This is for in case of Gerten-Pipking's law or second sound. Now we have these results concerning the polynomial and strong stability. So we assume H1. So this condition on L2 here, H1, under this condition, we have always, for the 4 cases, we have the polynomial stability, but for at least strong solution, because n is in n star and u0, so u0 is at least in the domain of A. So there exists a constant C such that the norm of the solution is more or equal than this quantity, where G here is equal to 4 in case of type 1, type 3, and second sound, and G is equal to 8 for Gerten-Pipking's law. So here we remark that we get weaker decay estimate in case of Gerten-Pipking's law than in the other 3 cases. For n equal to 0, that is for initial data in H, or which means that for weak solution, we have the strong stability. The limit of the norm of ut is equal to 0. But in this case, for n equal to 0, we have no decay estimate. We know only that the solution goes to 0. So we have a decay estimate starting n equal to 1. The K of proofs, in fact, is the following 3 known theorems in the literature. So here we denote by rho A and sigma A the resultant and spectrum sets of A. Then we have the equivalence between the exponential stability of P and these known conditions. So here the imaginary axis is a part of rho A, and this quantity is bounded. So we have the equivalence between the exponential stability and these 2 conditions. So if we want to prove the exponential stability, so in case of Gerten-Pipking's law and second sound, we prove that our hypothesis H1 and H2 are equivalent to these 2 conditions. So we have the equivalence between H1 and H2 and the exponential stability. For the polynomial stability, we have just to prove those 2 conditions So the first one, as in for the exponential stability, the same condition, but here we prove that this norm multiplied by lambda power minus g for some g in n star, with lambda, absolute values of lambda is bigger or equal than 1, is bounded. If those two conditions are satisfied, then we have the polynomial stability for any n in n star. So we have also here, in fact, the decay rate, which of the polynomial decay rate depends only on also on the regularity of the initial data, and also, of course, on the control, the considered control. For the strong stability, we have to prove two things. So the first condition, the same thing, that is, I has no imaginary eigenvalues, and sigma A intersection IR is countable. So we have the limit or the strong stability, that is, the solutions goes to 0 or converges to 0 when t goes to plus infinity. So what we prove here, first, I will try just to give a brief ideas of the proof, because as I said, it's very, very technical. So first we prove that H1, our hypothesis H1, is equivalent to this one. The imaginary axis is a part of row A. So according to the properties of our operator A, so we have just to prove this. So ker ai lambda I minus A equal to 0 for any lambda in R. For lambda equal to 0, this was done in the existence well-posedness part. So for lambda in R star, we have just to prove that this equation has only 0 solution, or has only one solution, which is u equal to 0. So we consider this equation. So we have this, the real part of this quantity is 0, because we have lambda is a real number, this is a number, and so we have I. This is equal to this, and as I indicated before, this is equal to this. And because here the quantity is here, each quantity is negative and equal to 0, so we conclude that theta equal to 0. So we use also the boundary conditions, eta equal to 0, q equal to 0, and thanks to the connection between phi, the first equation, and theta, we conclude that phi and theta, phi t is also equal to 0. So we get this. Now we Laplace in the other equations, we get this relations. So psi t is equal to I lambda psi, the same thing for w. Psi is equal to this number times w, and w satisfies this ordinary differential equation. So we have just to prove that w equal to 0. So we conclude that psi equal to 0, psi t equal to 0, and wt equal to 0. By solving this ordinary differential equation and using the boundary condition on w, we get that w is equal to this quantity sign, this quantity with c real number. So by contradiction, if we assume that c is equal different to 0, and using the boundary conditions, again the boundary conditions at 1, we prove that lambda satisfies these two equations. And by substituting, we prove that lambda does not satisfy our hypothesis H1. In the reverse case, we prove that we can get a solution W which is not equal to 0. So we arrive to prove that H1 and the first condition in the imaginary axis is a part of row A. Those two things are equivalent. Now for the exponential stability, we have to prove that H2, the second hypothesis, our second hypothesis is equivalent to this condition, the second condition of the theorem. So we prove this by contradiction. So we have to find sequences n in the domain of A, sequences of real numbers, such that we have these properties. So using different multipliers terms and integration by parts using boundary conditions, we arrive to prove that these properties, two or three properties, imply that the limit of the norm of un is equal to 0, which is a contradiction with the fact that the norm of u1 equal to 1 for any n. So this proves that, or this proves that this quantity is bounded. So h1 and h2 are equivalent, well, to this two necessary and sufficient condition for the exponential stability. So we have the equivalence between our hypothesis h1 and h2 and the exponential stability in case or in cases of Gerten-Pipkin's law and second sum. Now, for the non-exponential stability, we will prove that in case of type 1 and type 3, and also in case of Gerten-Pipkin's and second sum, such that H2 is not satisfied, in those four cases, this quantity is not bounded, is equal to plus infinity. So we have to find an example of sequences, lambda n in R, Fn in H, Un in domain of A, such that, well, the limit here is plus infinity. So this equation is satisfied. So in fact, the image of Fn by this operator is Un, and this the norm of n is smaller or equal than 1. And we arrive to we will, according in fact to the boundary conditions on the psi, phi, and w, we chose Fn and Un, sorry, like this, with well chosen coefficient a1 and a2 and alpha 1 and etc. And we arrive to construct this the sequences lambda n, Un, and Fn, which proves that this quantity is not bounded. So we don't have the exponential stability in cases of type 1 and type 3, independently of the parameters, and also in cases of Gerten-Pipkin's law and second sound if H2 is not satisfied. For the polynomial stability, we have yet proven that H1 is equivalent to this condition. So now we have just to prove that this quantity is bounded. Like in the case of exponential stability, we prove this by a contradiction argument. So we have to find the sequences Un, lambda n, etc. like before, but just here we have to prove that, well, this weaker condition, that is this condition, this limit is equal to 0, and here we have lambda n power g. G, of course, is given in our theorem, g equal to 4 in cases of type 1, of heat conduction of type 1, type 3, and second sound, and g equal 8 in case of Gerten-Pipkin's law. And similarly, by using different kinds of several multipliers and integration by parts, we arrive to prove that the limit of Un is equal to 0, which is a contradiction with this this property. So this quantity is bounded, and now we apply this Newman theorem to conclude the polynomial stability. The strong stability is already done, in fact, because well, we have this condition, and the properties of our operator A implies that, well, sigma A is intersection, the imaginary axis is countable set, so we have the strong stability. I will finish my talk by some issues and open questions. Here we can consider other kinds of boundary conditions like this. So here we have, for example, the second we have Newman boundary conditions for the first component at 0, and for the second and third component but at 1, and directly boundary conditions in the other cases. Here we have, in fact, the reverse of the situation I considered here, that is directly boundary condition for phi, and Newman boundary conditions for psi and w, or these boundary conditions. So the same results are valid in these cases. Also, our results for type 1 and type 3, that is, there is now exponential stability, but we have polynomial and strong stability. The same results can be obtained if we replace, well, this heat conduction by linear frictional damping, Q4 phi T, or an infinite memory term like this. These two cases were done by self. The results are published in this paper for infinite memory, and in this here in this paper for the linear damping. In cases of second sound and Gerten-Pipkin's law, we consider these two coupling terms between the heat conduction and the first component of Bresse system. If we replace this by delta theta and delta phi phi t, that is, we don't consider the derivative with respect of x. In this case, also there is now, we don't get, or the exponential stability does not hold independently of the parameters, even if for Gerten-Pipkin's law and second sound law. But of course, the strong and polynomial stability are still satisfied with weaker decay rate. Also, some polynomial stability estimates can be obtained in the unbounded domain, that is, when we replace the bounded domain 0,1 by R. So some polynomial, in this case, we don't get the exponential stability, but some polynomial stability are satisfied. This is it is now doing by my PhD student Zainab Muhammad Ali. Some open questions, interesting open questions in my opinion, is concerning the boundary conditions. So I indicated before some other kinds of boundary conditions which can be considered and get the same stability results. But here, if we consider the same boundary conditions for phi and psi, or for phi and w, at least at 0 or at 1, or we consider different boundary conditions for psi and w at least at 0 or at 1. In these cases, I don't know if we can prove some stability results. This is when we construct these sequences UN, Fn using cosine, sine, etc. So, well, this is here we have a problem to consider this this kind of boundary conditions, but maybe some stability result can be, or exponential or polynomial stability result can be obtained. For in case of Gerten-Pipkin's law, I consider the best class of kernel G, that is a kernel G which converges to 0 exponentially. So the question is open concerning larger class of kernels G which converge to 0 polynomially, that is less than exponentially. The last comment, or the last open question, which is in my opinion very interesting, is the optimality of the polynomial decay rate. So in these papers, the authors proved that the equivalence between these polynomial decay rate and these two conditions, but here we have the equivalence, not only this over lambda power m is bounded, but we have the equivalence between the norm and absolute values of lambda power m when lambda goes to plus infinity. So when we see or when we look to the proofs, my proofs in the, or our proofs in the, for the polynomial stability, we see that m cannot be smaller than 1, cannot be smaller than 1. So the decay rate cannot be, the polynomial decay rate cannot be better than t power minus 1. So we know that then, or this implies that the optimal decay rate of the norm of our solution, of our system. P is certainly between t power minus 1 and t power minus 1 over g, where g is equal to 4 in cases of a second sound, type 1, and type 3, and g equal to 8 in case of Garten-Pipkin's law. So finding the optimal polynomial decay rate is an interesting question, I think. Well, I stop here. Thank you very much for your kind attention.
Okay, thank you very much, Aissa. There is some questions. Please. Some questions. When you solve, there is, please. Where Youssef have a question. I don't know if
Hello.
Yes, I hear.
Hello, Aissa.
Hello, Whale.
How are you? I'm Whale Youssef, Doctor of Mathematics from Beirut, the Lebanese University, Lebanon. First, Aissa, I want to congratulate you for this nice presentation.
Thanks.
Very, very nice presentation. I have a question. Can we solve your problem in the case of locally distributed damping?
I didn't consider this case, but local frictional damping, maybe it can be done, maybe. I didn't do the computations or see this problem, but I think it can be done. However, for the Garten-Pipkin's law, that is for memory, local memory, I think is a very hard question. Even for just wave equation, simple wave equation with memory, it is not yet done. So for frictional damping, I believe, or it seems for me, it's that it can be done, or we can get similar results.
I think it's very hard to construct a Hilbert space.
Yes, yeah, this is particular problem. This is one of the particular problems generated by the case of local dissipations.
Okay, I have a very small comment also about your open problem 1. Can we see your open problem 1?
Yeah, this is concerning the boundary conditions.
Yes, you said the question is posed when phi and psi, etc., have the same boundary conditions. We have other methods to prove the non-exponential stability, using the so-called Whale Theorem.
I don't know this.
Of problems, in these cases, without constructing a sequence, we can prove the non-exponential stability. So I suggest you to try with this method. I'm sure you will get something.
Okay.
And
so if you have, I don't know, a paper or about this method, you send it to me. I don't know it. Yeah, it's nice.
There is a new publication for me in XAMPP. I treat the problem of Bresse, transmission problem of Bresse with thermoelasticity. And we have the detailed method. Also, you can see a paper for Rivera and Reinhardt. I think the name Reinhardt, your friend.
Rake.
Yes. Also, they treated these problems.
Okay, I will see this.
Especially using the Whale problem, the Whale method.
Okay.
Thank you very much, my friend.
Thank you to you.
Okay, thank you.
Thank you very much. There is some another questions. No. Then we thank Aissa for his presentation.
Thank you very much. Thanks to you.
Okay. Thank you very much.
Thank you, Mauricio. Thank you a lot, Professor Aissa Guesmia, for your amazing.
Thank you to you. Thank you to you again.